Now, we have the sine alpha, which is equal to the x-coordinate of the point of intersection with the unit circle. So let's look at it again. The point of intersection is P1, right? And its x-coordinate is the x1. So that means the sine alpha, okay, the cosine alpha is equal to this x1, and the sine alpha is equal to this y1. So now the sine alpha is equal to y1, and which is equal to y over r. And cosine alpha is equal to x1. This is x-coordinate of the point of intersection. And then this x1 is equal to x of r. So now, if we know the coordinates of one point which is not the point of intersection on this terminal side, we can use this pair of the coordinates to find the sine of alpha and cosine alpha in such a way. That is, the sine alpha is equal to x over r. R here is just equal to the square root of the x squared plus y squared. Right, that is the distance between the P and O. And the cosine alpha, that is equal to x over this r. So this argument can be repeated in each quadrant. Right now we just work in the quadrant 2. You can do the same thing for the other 3 quadrants, and it works. So that means we may just use the x, y, and r. R here, you write this again, is equal to the square root of x squared plus y squared to define the sine, cosine of alpha. And similarly, you can define the tangent. Tangent alpha is equal to y over x. And then cotangent alpha is equal to x over y. So that means if you know any point on the terminal side of the angle which is not the origin, then you always use the coordinates of this point to define the trigonometric function values of this angle alpha. And this is summarized in the theorem. Okay, so if the x, y is any point other than the origin on the terminal side of this angle alpha in the stand position, and r is the square root of x squared plus y squared, then you have the sine alpha equal to y over r, and the cosine alpha equal to x over r, and the tangent alpha is equal to y over x. Suppose x is not equal to 0. Okay, let's look at the one example on how to apply the theorem. And let's look at the problem 6 on the page 496. Assume that the alpha is angle in the standard position whose terminal side contains the given point. Find the exact values of the sine alpha, cosine alpha, tangent, cosecant, secant, and cotangent alpha. Okay. So right now we know one point on the terminal side of this angle alpha. Then we need to find the 6 trigonometric function values of this alpha. So this is page 496, problem 6. First, we have point P. This is the -1 and the negative root of 3. So that means we have the x equal to -1 and the y equal to negative root of 3. So let's first find r. R is equal to the square root of x squared plus y squared, and this is equal to the square root of square of the negative 1 plus the square of the negative root of 3, and this is equal to the root of 4, so that is equal to. Right. Then by that theorem, sine alpha is equal to y over r. So y is equal to negative root of 3, and r is equal to 2. So we get the negative root of 3 over 2. And cosine alpha, this is equal to x over r, and x is equal to negative 1. So you get the negative 1/2. And then tangent alpha, which is equal to y over x. So y is equal to negative root of 3, and x is equal to negative 1. So it's equal to root of 3. Then cotangent alpha, this is equal to x over y. So that is the negative 1 over the negative root of 3, and this is equal to 1 over root of 3. And you rationalize, then you get root of 3 over 3. Then secant alpha. Secant alpha is equal to 1 over the cosine alpha. And the cosine alpha is equal to negative, okay, this is the 1. Cosine alpha is equal to negative 1/2. Then finally get the negative 2. Right. Just flip this bottom to the top. Then cosecant alpha, which is equal to 1 over the sine alpha. So sine alpha is equal to negative root of 3 over 2. Then you multiply both the numerator and denominator by 2. This 2, this 2 cancel. So you get negative 2 over the root of 3. Then you rationalize. Then finally you get negative 2 times root of 3 over 3. Okay.